30 hertz. There is a 130 hertz frequency signal in it. And this 130 hertz is built with cosine, either cosine or sine. So if we apply a filter, and take this signal out, it's going to look like either a cosine or a sine wave. Now, a lot of the time when we apply FFT to random signals, we're going to get multiple peaks, right? The reason is for random signal, there are multiple frequency contents. It's very easy to build a signal with multiple frequency content. For example, we say we have a signal with cosine 10t plus sine 100t plus cosine 20t. Then we have 3 different frequency content in there. And if you do a FFT based on this signal, right? And if you did it correctly, you should be able to get 3 clean peaks at those 3 frequencies. Spectral leakage. Spectral leakage is especially related to FFT. The reason of existing for spectral leakage is because of limited observation. What do I mean by limited observation? Remember, we say for a Fourier series, our function always have to be periodic. Now, think about if we're feeding a random signal into FFT. A random signal is not periodic, right? A random signal is not periodic, and we're using our FFT algorithm. So we have a big assumption there. What is our assumption? Our assumption is whatever signal we use, we give FFT algorithm, we assume this piece of signal will repeat itself over time, again and again and again. That may not be true, but we make this assumption, otherwise we will not be able to apply FFT. And based on that, we have a problem, which is spectral leakage. Why spectral leakage occur? It is because when we have a periodic signal and we feed, for example, we have a sine wave. Of course, we know its period is from here to here. Now, our observation would go from here all the way to this point. For us, we know it's periodic, but when we do FFT, fast Fourier transform algorithm assumes this is a periodic function, and it repeats itself. So the next point will start here. In computer, the fast Fourier transform will think about, that repeats itself. But this is not true. So eventually what it causes, if we say this is a 10 hertz sine wave, what it causes is we do a FFT and we can see a peak at 10 hertz, but that's not all of it. We see something else. peaks, they are not true. There does not exist because we only have a 10 Hertz sine wave. We're supposed to get a clean 10 Hertz peak. The reason we have this is because our observation is not exactly one period of the signal. So this is spectral leakage. Now, a way to avoid spectral leakage is if we use observation of exactly one period of the signal. If we use exactly one period of signal, then our FFT is going to be single clean peak at 10 Hertz. Okay? Now, coming back to our random signals. For a random signal, we don't know what is the period. What is the period? Nobody knows, right? Because it's random. And we don't even know whether it's periodic. So, whenever you're doing FFT to a random signal, you're going to see a lot of spectral leakage. It's not something you can avoid. But you have to understand there is spectral leakage in your FFT. In addition, since it's a random signal, we don't know what is the frequency, what is the highest frequency of this signal. So, whatever you sampled with sampling frequency fs, whatever you sampled, that will be the one to determine the highest frequency you obtain from this random signal. Okay? Which also means we can never completely observe a practical signal. We can always observe up to certain frequencies. And that tells us one thing you should always keep in mind is our observation is always not enough. No matter what you do, our observation is always not enough. Okay? Alright. Some more example with spectral leakage. Okay? This is a periodic signal built with sine 10t cosine 20t. Now, we randomly pick. We say, okay, we take this piece of signal from 0 to 10 to 1 second. We take 1 second of this signal, and then we plot it. This is 1 second of this signal. Something like this. We can see it's periodic, but our observation is from 0 to 1 second, which is not exactly period of the signal. One period. Okay? So we apply FFT, and you see, multiple peaks, many peaks. This is our FFT, many peaks. Which frequency are we supposed to get for peaks? We know omega is equal to 2 pi f, right? So our frequency of the sine 10t is actually 10 divided by 2 pi, which is frequency is 5 divided by pi. Now our second signal frequency is 20 divided by 2 pi, which is 10 divided by pi. So we have two different frequencies. We should have two different frequencies, two different peaks, clean peaks, at those two different frequencies. This unit is hertz. But due to spectral leakage, we're not getting it. Now, next one I want to show you. Let's calculate the what is the period of this signal? Sine 10t, cosine 20t, what is the period? The period for sine 10t is 2 pi divided by 10 is pi over 5. The period for cosine 20t is 2 pi divided by 20 is pi over 10. So, our total period of the signal, it should be pi over 5. Right? Okay, let's go back to our program. Change our observation from 0 to pi over 5. How's like that? We change our observation. We go from 0 to pi over 5. Now you see a complete period. This is our observation. And if we apply FFT, this is what we get. 2 very nice clean peak. Okay, now we want to talk about digital filters. Filter types. First, we want to talk about filter types. What kind of filters do we have? We have low pass, high pass, band pass, and band rejects. Based on the names, you can think about low pass filter. Lower frequency will be able to pass through the filter, and higher frequency will be filtered out. And high pass filter, lower frequency will be filtered out, and higher frequency will be passed through. Band pass, only a certain band of frequency will pass through, all the other frequency will filter out. Band reject, a certain band of frequency will be filtered out, all the other frequency can pass through. So, 4 types of different filters. Now, based on the different constructions, we have different types of digital filters. Each of these 2 types, they can be used to build either a low pass or a high pass or a band pass, band reject. Okay? The first one is FIR, finite impulse response filters. Okay? Basically what it does is, it is a digital filter who has an impulse response in a finite duration. Which means the transient response of this filter is finite. Now, IIR, infinite impulse response filter. Based on the name, the impulse response is going to be infinite, which means the transient response will not stop. You always have some transient response. Now this you only need to know a little bit. You only need to know there is 2 types, FIR, IIR, and then we'll talk about filter specifications. How do we specify a filter? For example, we talk about a low pass filter. This is the frequency, and this is our amplitude. A low pass filter will always want to have lower frequency pass through and higher frequency filtered out, right? So we have pass band. And stop band. This is transition band. For an ideal filter, we want our transition band to be 0. For an ideal filter, we want a response like this. This is an ideal low-pass filter. Low pass. This is an ideal low-pass filter. We want our transition band to be 0. But for real filters, we can never achieve. We can never achieve. With a very, very high order filter, we can achieve something very close.